Hi, welcome to my presentation on budgeted training. This is Martin Lee from Carnegie Mellon University. In this talk, we will look into the problem of training deep neural networks under resource constraints. Let me start with resource constraints. Nowadays, it's common to train on very large datasets, and their sizes keep growing. We can imagine that future datasets might be magnitudes larger than what we have today. On the other hand, the compute we have is usually limited. For those gigantic datasets, training even one single epoch might not be feasible. What makes matters worse is that we are often not satisfied with training just one epoch, because we need to tune hyperparameters and search for the optimal neural architectures. Both require repeated training. Normally, when we train a model, we want to know what the best achievable performance is on a particular dataset. For example, one often asks such a question: how good is ResNet 50 on ImageNet? In this work, we decorate this question with budget constraints. For the same example, now we ask, how good is ResNet 50 on ImageNet within the allowed budget? Then the following question is, how to quantify this budget? One can represent it in total training time, compute hardware, or simply the cost spent on training. We choose the number of iterations as a representative resource. This allows us to abstract out the specific constraint without loss of generality, since any of the aforementioned constraints could be converted to training iterations. The key difference of our setting and the standard setting is that our setting is non-asymptotic. Instead of optimizing over the loss as iterations go to infinity, we optimize for the loss at a specific budget or iterations. Given this new goal, it's clear that we should train the model in a different way, but how? We answer this question through the perspective of learning rate schedules. We pick this perspective for two reasons. First, we found that the schedules are often tied with convergence analysis in the classic setting. When asymptotic convergence does not make sense, learning rate schedules also need to be revisited. Second, our experiments suggest that it is practically very effective and more effective than previously proposed approaches like data subsampling. From this perspective, we propose a simple solution, which is budget-aware schedule of linear decay. No matter the given budget, we always start with 100% of base learning rate and decay proportionally to 0 at the end of the training budget. The form of linear decay is historically used in simulated annealing, and we borrow it here for its simplicity. Here's the intuitive comparison of our proposed solution and the standard approach. We see that training loss decreases smoothly and steadily on the linear schedule. The accuracy at the end of each budget is also much higher than the off-the-shelf counterpart that is budget unaware. For example, given 10% of the training epochs, budget-aware linear schedule is able to achieve 90% of the full budget accuracy. Now let's look at the practical performance on CFR10. First, for the regular full budget case, all schedules, except for constant learning rates, deliver similar performance. This is not surprising, given that they are designed and tuned for this setting. But as we start to constrain the allowed budgets, the advantage of linear schedule emerges. For example, at 1% of the total budget, the same linear schedule outperforms all other schedules. We found that the linear schedule is effective across different budgets. To show that the conclusion generalizes beyond the small toyish CFR10 datasets, we have conducted extensive experiments on standard vision benchmarks. This table shows the experiments of ImageNet classification. The results are similar to CFR10 case, except the performance gain is more significant. We further conduct experiments on 4 additional vision benchmarks with state-of-art models, and we observe similar conclusions. These experiments suggest that linear schedule is effective across tasks and architectures. We also did some analysis on what the desired properties are for budget-aware schedules. We found one of them is budget convergence. a phenomenon that as the learning rate vanishes for budget-aware schedules, so does the gradient magnitude. If you want to learn more, you can check out our paper or our project page. Thank you.